One of the services an operating system needs to provide are timers. Various independent processes will ask to suspend or be notified a certain amount of time later, and the OS needs to keep track of those. Now, a data structure to track timer events has its work cut out for it. For one thing, it needs to know when the next timer expires, and it needs to know this efficiently. It just wouldn't do to spend lots of time trying to figure out when the next timer expires. So which data structure shall we use for that? And how do we know how well it will behave? To answer that, let's talk about complexity and big O notation. Complexity analysis is an attempt to model how a data structure's performance is affected when the number of elements in it increases. Let's illustrate this by saving our timer events in a linked list. We'll keep the list sorted by inserting each new timer event after all elements earlier than it and before all elements later than it. So, at any point in time, reading the linked list in sequence will give us the elements from earliest to latest. In order to do performance analysis, we need to specify which are the operations that are of interest to us. For our timer list, we're interested in the following operations: inserting a new element into the list, removing a cancelled event from the list, locating the earliest event in the list, and removing the earliest event from the list after it's handled. Let's begin with op number 2. How fast can we remove an event from anywhere in the list? The answer is, of course, it depends. The quality of the code written, the programming language used, the compiler and compilation flags, and the machine on which the code is run can all affect how fast this operation is, sometimes quite dramatically. As such, you might be tempted to say that we cannot perform the analysis. There is something we can analyze, however, without knowing any of those factors. This is, how does that time change as a function of the total number of elements in the list? If we look at event removal, we can make sure that the entity asking for the timer cancellation has a pointer to the element being removed. Removing an element from a linked list is just a matter of linking the following and preceding elements to each other. We need not concern ourselves with any other element in the list. As such, we can say with confidence that the performance of removing an element is not affected by how many elements are in the list in total. We mark such performance characteristic as O of 1. O is the function giving us the performance of the task, and 1 is not a function of n, which we use to denote the number of elements in the list. Since O of 1 is not dependent on n, this is also sometimes called constant time algorithm. So let's look at one more operation, inserting a new element. In order to insert a new element, we need to scan the list until we find the correct insertion point. How long that takes depends on how many elements are already in the list. We might get lucky. If we happen to get the registration request in reversed order, every insertion will happen at the very beginning of the list, and we won't have to scan any elements at all to find the insertion point. So we can say that insertion is O of 1 as well? I think everyone understands that this approach is too optimistic to be useful. In particular, when we talk about big O notation, we are referring to the worst case. In our case, the worst case would be inserting the timeouts in order, from earliest to latest. In such a case, we'd need to scan all existing elements in the list in order to find the insertion points. So our work will be double if the number of elements will double. This last sentence, a linear relationship between the amount of work and the number of elements, is notated as O of n. As can probably be guessed, we prefer O of 1 data structures over O of n ones. So if we store the timeouts in a linked list, insertion is O of n, cancellation is O of 1, and expiry is O of 1. Let's see if we can do better. When talking about timeouts, everyone's go-to algorithm is a priority queue. Without going too much into how it works, we'll just point out that it's a tree. With trees, each level of the tree has n times more elements than the level above it. So, for example, A balanced binary tree will get a new layer when we double the number of elements in the tree. To insert a new element into a tree, we need to traverse all the layers, worst case, remember? This means that if we double the number of elements in the tree, we add a constant amount of processing time. Such ratio is symbolized by the notation O of log n. So comparing a priority queue to a linked list, we get the following performance analysis. Inserting a new timeout O of log n for a priority queue, O of n for a list. Removing an element, O of log n for a priority queue, O of 1 for a list. So which is better? O of 1 for removal and O of n for insertion, or O of log n for both? Let's check an example. Suppose we have 1000 register events and we would like to add another. For the list, we'd need O of 1000 operations. For the tree, we'd need O of 10 operations. For the removal of the list, we'd need O of 1 for the list and O of 10 again for the tree. I think it's fairly clear that the tree is much preferable. But there's an even better data structure. It's what the Linux kernel uses, for example. It's called Cascaded Time Queue. At least, that's the name that I was introduced to it as. I have been unable to find any references to it under that name, nor under any other name. If you do know of a standard name for it, feel free to drop me a note in the comments. Feel free to sound as smug as you like about it. You've earned it. Here's how that data structure goes. We decide on a basic time resolution to track. This can be as accurate as we like. So let's say we want to allow tracking of timer events in 1 microsecond or 1 over 1 million of a second resolution. We initialize an array of buckets, each representing 1 millisecond time slot. In each bucket, we keep a linked list of all the events registered to expire during that microsecond. So if that array is of, say, 256 buckets, we can keep track of 256 microseconds. Okay, that kind of sucks. So we can add another array, a second array. This array has a lower resolution. Each bucket in that array corresponds to 256 microseconds. In other words, each bucket in the second level array covers the same time frame as the whole first level array. If this array also has 256 buckets, we now cover 65,536 microseconds, or around 65 milliseconds. While better, it's still highly likely that we're going to need more than that. So we add a third array. Each bucket in that array holds, you guessed it, 256 buckets, each covering 65.5 milliseconds. This array covers over 16 seconds. Of course, even 16 seconds aren't enough, so we can add a fourth array. This gets us to almost 4,300 seconds, or about an hour and a half. And a fifth array will get us to 12 days. At which point, we can assume that events scheduled for more than 12 days are rare, and use a single overflow list to capture any event too far in the future to be in the list. A slightly less robust, but which generates simpler code, is to just add layers until the coverage is more than we'll ever need. And so a sixth layer will get us to almost 9 years, and a seventh layer to over 2,000 years. At this point, just issue a check to be cashed by anyone asking for a timer event beyond 2,000 years and not getting woken up in time. Terms and conditions may apply. So we have 7 layers, each of an array of 256 linked lists. That sounds like a lot, but it's actually only 1,792 lists. Assuming each list is composed of two 64-bit pointers, it's around 28 kilobytes. Nothing a modern CPU can't easily handle. My implementation actually needs half of that, but that's for another video. Of course, if that's a problem for you, you can use arrays of just 16 lists. With 13 layers, you can cover 142 years, and that only needs 208 lists, or 3.3 kilobytes. Of course, some overheads depend on the number of layers, so such an array may perform more poorly. Slightly. So how does this cascaded time queue actually work? We have a current time. Whenever a new event is registered, we find the lowest level in which it still applies. If it's in the next 256 microsecond, it may fit in the lowest level, but otherwise we'll probably have to climb at least one level to find the right bucket for it. Of course, as we climb levels, the event's timeout bucket will become less and less precise. Every 256 microseconds, our first level expires. When that happens, check the next level. If that has not expired, we take all the events stored in it and distribute them to the correct buckets in level 0. But every 65,536 microseconds, the second level also expires. When that happens, we need to go higher, and every so often, even higher. Of course, now we need the whole thing to tick, to wake up every microsecond to check on the array. These wake-ups are a huge overhead. One solution is to reduce the resolution of the buckets, but this also reduces the accuracy of the wake-ups. A much better approach is called tickless operation. The idea is that when the OS is idle, it checks when the next event is expected and goes to sleep for that amount of time. So our cascaded time queue now has to be able to tell us when the next event is due. To do so, we need to scan level 0 from the current bucket until the end and look for non-empty list. If none is found, we scan level 1 from the current bucket until the end again, looking for a non-empty list. If none, level 2, and so on. Our absolute worst case is that there are no more events in the array, in which case we will need to scan 1,792 buckets. That's it. It's not a small number, but bear in mind that this only happens if the system has nothing to do anyways. Let's analyze the complexity of our main operations. Entering a new event into the cascaded queue requires finding out where it is. Our worst case on that front is that we need to go through all the levels, which would require the same number of operations as there are levels. Since that number does not change based on how many elements there are in the array, I'm going to call this constant. It does feel a little like fudging the numbers, but please believe me that not by a lot. So we'll call insertion constant time. How about cancellation? If we keep a pointer to the element being cancelled, we can do that in a constant time, same as for a simple linked list. Removing the first element is a little trickier. Actual removal is, of course, constant time. Finding it, however, is a little more complex. Finding the earliest non-empty list is constant time, for much the same reason as before. However, assuming this bucket is not the first level, distributing all the elements in that bucket back to the lower levels is linear with the number of elements. The worst case, which remember is what big O notation is after, is that all the elements of the entire container are all in this one bucket. So advancing the time is O of n. Oops. So on first glance, this is nothing more than a glorified linked list. For a linked list, we take O of n to insert an element, whereas here it's finding the first element that needs O and n, but surely this is a distinction without a difference. We have an O of n container on one hand and a tree which is an O of log n on the other. We've already established that O of log n on all operations is better than O of n on just one, right? As you can imagine, things are a little more complicated than that. To understand why, let's ask what is the worst case for finding the first two elements of the container. We've already seen that the worst case for one element is that it is stored in a bucket on level 6, along with every other element in the array. Getting to it will require first distributing all the elements in the container to their location, an O of n operation. But when we then check the immediately following element, we find that it cannot also be in the same bucket as every other element. By this point, the highest level this second element can be in is level 5, as the previous step must have distributed it as well. But this analysis is still lacking. While element 2 may not be in level 6, it can still be in level 5 along with every remaining element, which means that handling element 2 would still require us to handle n-1 elements, which is still O of n. Employing the same logic, however, tells us the third element must be at most on level 4, and so on. Let's look at it from another direction. Obviously, element 3 does not need to be at most on level 4. It can positively, absolutely be on level 6. If it is, however, it means that it and all elements after it were not part of the same level 6 bucket as the first element. If handling the first element requires handling all other elements in the container, the complexity handling of those elements when their time comes is by necessity reduced. We can take our worst case, O of n, hit over the first element or over the second element, but never both. Does big O notation care about this? Not even a little. The big O complexity of a cascaded time queue is O of n, same as sorted linked list. But while big O notation isn't affected by this, performance obviously is. Which means that new complexity calculation, one that does take this into account, may be useful here. If you go back to our example, what we notice is that each element, when viewed in isolation, has an O of n worst case complexity. This view only changes when we realize that this worst case does not compound when handling multiple elements. So instead of asking about the big O complexity of handling a single element, let's ask about the big O complexity for handling all the elements. What's our worst case of inserting, finding, and handling all n elements of the container? Of course, that value isn't really interesting. We're not handling all elements at once. We're handling them one at a time. To get a more useful notation, we take this big O notation of handling big N elements and divide the result by big N. This is called amortized complexity. Before we look at the cascaded time queue case, let's look at the linked list example again. What's the complexity of inserting big N elements into a sorted linked list? Answer: the worst case for each such insertion is O of little n, where little n is the number of elements already there. So the complexity for inserting all big N elements into the list is the sum of the arithmetic progression running from 0 to big N minus 1. The formula for this is the mean between the first and last elements multiplied by the number of elements. In our case, we need to skip 0 elements to insert the first element, and we need to skip n minus 1 elements to insert the last one. So the total number of scans in the worst case is n squared minus n divided by 2. Except there are some aspects of this expression that complexity simply doesn't care about. Take the division by 2, for example. Different implementations, programming languages, and hardware may have different performance characteristics. To try and not account to them, multiplying or dividing by a constant is not interesting to us. The division by 2 is just not important. Perhaps surprisingly, the same goes for the subtraction of n. Big O complexity cares about what happens when the container sizes increases. As that happens, n squared will be so much bigger than n that it becomes insignificant. So despite the fairly precise answer we got, the big O complexity of inserting n big N elements into a sorted linked list is O of n squared. Divide that by big N, and you get that the amortized complexity of inserting an element into the sorted linked list is O of n. In other words, the linked list has a big O complexity and an amortized big O complexity that are the same. So now let's look at the cascaded time queue again. The interaction between the operations are a little hard to analyze. Thankfully, we can take a completely different approach. Instead of asking how many elements must we handle when we do operation X, we can ask how many times will each element be handled throughout its lifetime. It turns out that has a very straightforward answer. Each element will be handled once when it is inserted into the queue. The worst case is that it is inserted into the highest level, which is level 6. During its lifetime, it would then need to be handled at most 7 more times. Once as it is inserted into each consecutive lower level, and once more when it expires and is removed from the queue. For a queue with 7 levels, each element's worst case is that it will need to be assigned 8 times. So the absolute worst case for handling all n elements of the queue is O of 8 times n. Divide that by n, and you get an amortized complexity of O of 8. But remember, we don't care about constant factors. The amortized complexity of the cascaded time queue is O of 1. Here's the thing. In practice, The amortized complexity of an algorithm affects performance much more than its big O complexity. Localized latency spikes are something most systems will happily pay to get an overall better performing system. Which means that a priority queue with its O of log n, both big O and amortized, is no match for the cascaded time queue with its constant time amortized complexity. It's very tempting to think of amortized complexity as the average complexity. It certainly carries a lot of average equalities, including the division by the total number of elements. In practice, that's not exactly the case. Amortized complexity is only about performance interaction between the elements, where spending a lot of time on one element by necessity means that the next element will be very cheap. I'm going to be using the cascaded time queue as part of Saros, the operating system I'm implementing for the RISC-V control CPU. The specific implementation is part of a library called Fibers. It's available from my personal GitHub page. There's a link in the video's description right above the link to my Patreon page. I'm hoping it grows to be very useful, all told. The library, not the Patreon page. Well, that too, obviously. I'm going to be using Fibers as part of the SAR 1541 project, so feel free to keep a bookmark and maybe add a star if you're so inclined. In the meanwhile, thank you for watching. I'll see you next time.